Okay, so number one, find the area of a circle with a radius of 3.6 times 10 to the 4 millimeters or 36 times 10 to the 3 millimeters. Can you see that they are the same number? 3.6 times 10 to the 4 means I have to actually move the decimal point 4 places to the right to get it to where it should be. So if I shift it one place to the right to here, then I've only got 3 more to go, and now it's in engineering notation. So to do that, area is pi r squared for a circle, a familiar formula to you, I hope. So all I do in the calculator is hit the pi button, multiply that by 3.6, don't need to put any brackets in, hit the times 10 to the button, so that's a button, not multiplied by 10, times 10 to the, and then 4 if I'm using that particular one, and then hit the squared button, and I'll get the answer, which is, anybody? 407 4079. Is there a decimal point in there anywhere? Right, okay. An appropriate number of significant, is anyone agree with that, by the way, because I've not got a calculator here, so yeah, right, so that looks right. What about an appropriate number of significant figures? What would we say? How many significant figures in the number we put in? 2. So in the answer, 2, maybe 3. And because that's, so the third significant figure would be at this point here. That's the third significant figure. So I'll probably keep to that. So in other words, it would be 407. And then I'd fill in the rest with zeros to keep the place. But of course I wouldn't do that. What would I do? Times 10 to the something, yeah. Going lumps of 3. So go back. This is where it is. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll probably go to 4.07 times 10 to the 9. What would the unit be? Millimeters squared. A square millimeter is a very small unit, so that's why it's such a big number. So that's the sort of process I'd expect you to go through. You might decide to change the unit, but let's not talk about that particularly at the moment, because that's rather an awkward answer in square millimeters. But as it stands, I wouldn't leave that as the answer. Far too many decimal places, significant figures. I wouldn't write my final answer like that, even though that's the 3 significant figures now. I'd use engineering notation. I've left one thing off the end of this that I should have put on. What's that? Yeah, 3 significant figures. If I am going to round, don't forget to say that you've done so, okay? That's number 1. Number 2, round that to 3 significant figures. Answer, somebody? 3.7, only 2 figures there, so what do I put after? Right. Did you say that? Sorry. 3.70, well done. So 3 significant figures. So in other words, what we're saying here is, because we've quoted 3 significant figures, I'm saying that that 0 is measured, it's significant. And so that would be this round to 3 significant figures. Because this is a 9, this is the 3rd significant figure. So because of the next one, which is a 5, I'm going to round up. Because that's a 9, it means effectively this 69 becomes 70. Okay? So that's it. That's the tricky sort of one when you're rounding. What happens if that's a 9? It goes up to 0, effectively. Last one. Ohm's law. V equals IR. So I've got to multiply the current by the resistance. What do I do about the units? This is where engineering notation is so convenient. All you have to do is remember that milli is times 10 to the minus 3. So this is 0.36 times 10 to the minus 3, and that's exactly what I put into the calculator. And then I have to remember that mega is times 10 to the 6. So that's 2.4 times 10 to the 6 ohms. You need to remember these prefixes. So now in the calculator I type in 0.36 times 10 to the minus 3, using that times 10 to the button, multiplied by 2.4 times 10 to the 6. If I was writing this down, I would put brackets round, but I don't need to put the brackets into the calculator. And I get volts, 864 volts. Yeah, you did strike lucky there, yeah. Yeah, because you're timesing it by 1,000, you effectively got rid of the 1,000 on here, and then that means that that's a minus 3, and that's a 3, and they cancel each other out because of that 1,000. So that just struck lucky, it cancelled them out. Yeah. Okay. Questions on that? You need to be able to do those comfortably. You know whether you can do them comfortably or not. I'm not going to take this one in, it's only out of 3, but make a note if you need to look back at any of this stuff. Right, let's have a look at the aim for today then. We're going to move on and use formulae to find the area and volume of some shapes. The aim is to get us going on the first assignment question, which is to find the surface area and volume of some compound shapes. So, actually, I want to start off by looking at an example. I want to focus on setting out the problem. So, setting out the problem, and when it comes to the assignment, that's important because when you hand in the question, it needs to be laid out as you would lay it out to hand it to someone at work in an engineering environment in the form of a report. So I need to be able to understand what you've done. If I look down through a load of gibberish and I see the answer at the bottom and it's correct, it's still going to come back to you because I can't follow your logic. I need to be able to follow your steps. So that's important. So we'll have a look at an example. You don't need to follow that particularly, but I'll show you how I might do it. Okay? Obviously, I'm not saying you must do it like that. We'll focus on a formula. So we may need to have to rearrange a formula to use it. The units are going to be important, and then we'll think about the accuracy that you think at the end when you give in your final answer, significant figures, stuff like that. And there are some answers in the textbook, questions in the textbook, so I'm going to quickly now go through an example, and then I'm going to let you get on with some questions. I'm not going to stand here talking all the time today. So let's look at an example. Let's say we're going to find the surface area of a shape like that. Okay. So I need some dimensions. I'm told that the diameter of the circle in the middle is 4 centimeters. I'm told this dimension is 6 centimeters. This dimension is 8 centimeters. This dimension is 20 centimeters. And this dimension is 12 centimeters, say. Okay? Actually, it's a bit out of proportion there, doesn't it? Let's make that 9 centimeters. And it looks a bit more. Okay? So, how are we going to set about doing this problem then? Right, divide into two squares. How do you know they're going to be squares? Right, so what word would you use instead of squares? Two rectangles. I think that's what you mean. Yeah? Yep. Next, what are we going to do? Carry on with this plan? Right. That's sort of part of dividing into two rectangles. Yeah, okay, then, yeah, determine missing sides. Yeah. By the way, that's a hole. Yeah. Yeah. You're told the diameter is 4 centimeters. Yeah. Right. Yeah. So you work out, find the area of the circle. And then what? Go on. Yeah. So therefore, find area of two rectangles. Yeah. Anything else we need to do? I think this. Right. Yes. That was what I was waiting for. The obvious thing is obviously subtract area of circle. That might be an appropriate start to your report, isn't it? Just write out your plan, what you're going to do, so it's clear. Not only clear to someone who's reading it, but you've sussed out in your own mind the steps you're going to take to do this thing. Okay. Then what do we do? Follow the plan. Divide into two rectangles. Presumably down here. What would you do now then? So you divide into two rectangles, determine the missing side. So can you tell me about this one? This one here. 5, 11. Who said 5? Right. 11. And what else do we need? That's it, isn't it? Yeah. So now we can find the area of a circle. We've got the formula for the area of a circle. So maybe as an aside now, we'd say, right, okay, area of rectangle 1. So I'd possibly label them. This is rectangle number 1. This is rectangle number 2. So I can then find area of 1, area of 2. Equals 8 by 12, sorry, 8 by 9. 9 8 is 72 square centimeters. Area of 2, area of circle, subtracted. Okay. So that's the sort of thing we might do if it was a compound shape. So look at these formula for the area for the areas of common shapes. Page 146. Let's just have a quick look at these. Area of a parallelogram. Base times height. If you look at it, base is the length of the bottom side, but the height is something called the perpendicular height. And if you look at the triangle, the area of a triangle is half base times height, perpendicular height. Trapezium, area is half a plus b times the height, perpendicular height. So in all of these columns, this height means the perpendicular height. And this is a recognized abbreviation for perpendicular height. Perpendicular. And that's sort of vertical to the horizontal. So, you know, if you use the plumb line in a building, what you're doing is finding the perpendicular height, the vertical height, at right angles to the base. So that's what this symbol means here. It's a little right angle with an R, perpendicular. So we're after the perpendicular height. And if you look at these examples, say this top one here, if I wanted to find the perpendicular height, that's this height down here. That's the perpendicular height there. That's easy to see, and the perpendicular height here would be down there. In each case, what we're doing is forming a little right angle triangle, and we're after the vertical side of that right angle triangle. So quite often we've got a situation where we've got this side and this side, and we want to find this side. So what is it that we use to do that? Pythagoras. So we have to use Pythagoras theorem. To find that missing side, A. And Pythagoras' theorem says that A squared plus B squared equals C squared. The square of the two shorter sides equals the square of the longer side, called the hypotenuse. Yeah. So in other words, we need to use this theorem quite often to find this missing side before we can find the area. We would have to rearrange this formula to find A. At the moment, it's set up to find C squared. So what would I do to rearrange this formula to find A? Take away the B squared, someone says. A squared equals C squared minus B squared. Subtract B squared from both sides. Now we've got A squared. What do I do to find A? Square root. It's the opposite of square, square root. So therefore, A equals the square root of C squared minus B squared. A common formula that people use to find this perpendicular height. And you can do that in one hit on the calculator. So let's say I had this right angle, triangle. This side is 13. This side is 5. Find the missing side in one hit on your calculator. So hit the square root button and then put C squared, which is 13 squared, minus 5 squared, and then hit OK, and you should get the answer straight off. You should get 12. Yes, Lee? Good. Okay. If we look at the rest of these formulae, area of a circle, note the familiar form pi r squared. Quite often in engineering situations, you're given the diameter, as you are in that example we looked at. The diameter is 4 centimeters. So a lot of people, instead of using pi r squared and going to the trouble of halving the diameter to get the radius, they put the diameter straight into this formula, pi d squared over 4. And I'll leave that for you to understand why that formula is the same as that. If you think about that, I think you'll be able to see that they are actually the same formula. So you could use pi d squared over 4 if you know the diameter. Semicircle, not surprisingly, it's half pi r squared because it's half a circle. Look at the next one. This is an interesting one. Theta over 360 times pi r squared. Or a half r squared theta in radians. We'll be talking about this idea of radian measure in a few weeks' time. Let's look at this particular bit of it now and see how that makes sense. If you think of this sector of the circle going round angle theta here, it's that fraction of the whole circle interested in. Well, what's a whole circle? 360 degrees. So theta over 360 gives us the fraction of the circle that we're interested in. So let's say theta is 90 degrees. That's a quarter of a circle. Then 90 over 360 is a quarter. So that's the quarter of the circle. So your quarter times by the area of the whole circle will give you the area of the sector you're interested in. So that's where that formula comes from. The ellipse, and that's the formula we would just use. So pi times area, A times B rather, where A is the major axis and B is the minor axis of an ellipse. Not a common formula, but if in your environment you're using fuel tanks and stuff that had that sort of cross-sectional area, then you'd use these formulas. But I wanted to point out to you that actually a lot of them are self-explanatory. You don't need to remember them. You can work out what the area of a semicircle and the sector of a circle is, knowing the area of a circle. So use those, and there's exercise that follow on from that in this particular chapter 18 to find the areas of shapes. So if we look ahead to page 148.9, you'll see an exercise. I'm just going to give you a period of time now, about a quarter of an hour, 20 minutes, to have a go at some of these, and then we'll stop and have a look. Okay?